Hello everyone, welcome to our video lecture. In this video, we are going to talk about one of the most important components in analog electronics, the operational amplifier. Throughout this presentation, we will explain what an operational amplifier is, how it works, and we will analyze the most important performance parameters using the LM741 as our reference device. In addition, we will not only focus on theory, but we will also support our explanation with simulations in order to verify that the real behavior of the amplifier matches the values specified in the manufacturer's datasheet. By the end of this video, you will have a clear understanding of how this device works in real circuits and why it is so important in electronic engineering applications. An operational amplifier, commonly known as an op-amp, is a high-gain electronic device that amplifies the difference between two input voltages. It has two input terminals, the non-inverting input, which is marked with a positive sign, and the inverting input, which is marked with a negative sign. The output voltage depends on the difference between these two inputs and the gain of the amplifier. This relationship can be expressed mathematically as the output voltage being equal to the gain multiplied by the difference between the positive and negative inputs. Operational amplifiers are extremely useful because they can perform mathematical operations such as addition, subtraction, integration, and differentiation. Because of this versatility, they are widely used in many applications, including signal processing, control systems, active filters, and audio electronics. To better understand how real operational amplifiers behave, we first need to consider the concept of an ideal op-amp. In theory, an ideal operational amplifier has perfect characteristics. It has infinite gain, meaning that it can amplify any input signal without limitation. It also has infinite input resistance, which means that it does not draw any current from the input source. Additionally, it has zero output resistance, allowing it to deliver energy to any load without losses. However, real operational amplifiers do not behave in this ideal way. Devices such as the LM741 have several limitations due to internal mismatches between transistors, temperature variations, and physical constraints of the materials. For example, real op-amps have finite gain, non-zero offset voltage, limited input and output voltage ranges, and other non-ideal characteristics. These limitations must be considered when designing real electronic circuits. Now, focusing on the LM741, it is a general-purpose operational amplifier that has been widely used for many years. It is especially popular in educational environments because it allows us to clearly understand the behavior of real op-amps. The LM741 typically operates with a dual power supply, such as plus and minus 15 volts, although it can work within a range of supply voltages. It is a robust, stable, and reliable device that can be used in many applications such as amplifiers, filters, and signal conditioning circuits. Even though there are more modern operational amplifiers available today, the LM741 remains an important reference for learning purposes. One of the most important parameters of an operational amplifier is the input offset voltage. This parameter represents a small voltage that must be applied between the inputs in order to make the output equal to zero. Ideally, this value should be zero, but due to internal imperfections, it is not. For the LM741, the typical offset voltage is around 1 millivolt, and it can reach values of approximately 5 to 6 millivolts. This parameter is especially important in precision applications because even a small offset can introduce significant errors in the output. Another important parameter is the supply current, which indicates how much current the amplifier consumes from the power supply. For the LM741, the typical supply current is about 1.7 milliamps, and it can go up to around 2.8 milliamps. From this value, we can estimate the power consumption, which is typically between 50 and 85 milliwatts. This is important in applications where energy efficiency is required, such as battery-powered systems. The common mode rejection ratio, or CMRR, measures how well the amplifier rejects signals that are common to both inputs. In an ideal amplifier, only the difference between the inputs should be amplified, while any common signals should be completely ignored. For the LM741, the CMRR typically ranges from about 80 to 95 decibels. A high CMRR is important because it allows the amplifier to reject noise and interference. The power supply rejection ratio, or PSRR, indicates how sensitive the output is to variations in the power supply voltage. Ideally, changes in the supply voltage should not affect the output signal. For the LM741, the PSRR typically ranges from about 86 to 96 decibels. This parameter is important in systems where the power supply may not be perfectly stable. The open-loop gain of the LM741 is extremely high. It can reach values of approximately 200,000. However, in practical circuits, this gain is controlled using feedback networks in order to obtain a stable and predictable behavior. The supply voltage range is another important parameter. The LM741 typically operates between plus and minus 10 volts and plus and minus 15 volts, although it can tolerate higher values within specified limits. It is important to operate the device within these limits to ensure proper performance and avoid damage. The output voltage swing refers to how close the output voltage can get to the supply rails. In the case of the LM741, the output cannot reach the exact supply voltages. For example, with a supply of plus and minus 15 volts, the output typically reaches around plus and minus 13 volts. This limitation must be considered in circuit design. The maximum output current is approximately 25 milliamps, which determines how much load the amplifier can drive. The input voltage range defines the limits within which the amplifier can operate correctly. For the LM741, this range is typically around plus and minus 12 to 13 volts. Temperature is also an important factor. The LM741 can operate over a wide temperature range, depending on the version, and temperature variations can affect its performance. To validate these parameters, we performed several simulations. First, we implemented a non-inverting amplifier configuration in order to verify the gain. Then, we increased the input signal amplitude to observe the output saturation and confirm the output voltage swing. Finally, we applied a step input signal to measure the slew rate, which represents how fast the output can change. These simulations allowed us to confirm that the behavior of the LM741 matches the specifications provided in the datasheet. In conclusion, the LM741 operational amplifier is a fundamental component that helps us understand the behavior of real analog circuits. By analyzing its parameters, we can design more accurate and reliable electronic systems. Understanding these characteristics is essential for any engineer working in the field of electronics. To better understand the behavior of the LM741, we performed a DC operating point simulation using a voltage follower configuration. In this setup, the output is directly connected to the inverting input, which forces the amplifier to operate in a closed-loop condition with unity gain. In the first simulation, we set the non-inverting input to 0 volts. Ideally, the output should also be exactly 0. However, as we can observe, the output shows a small voltage of approximately 1 millivolt. This value corresponds to the input offset voltage of the LM741, confirming that even when the input is 0, the amplifier produces a small error at the output. In the second simulation, we measured the current flowing into the non-inverting input. We can see that there is a small current in the order of nanoamperes. This represents the input bias current, which is another non-ideal characteristic of real operational amplifiers. Similarly, in the third simulation, we measured the current at the inverting input. Again, we observe a small current, slightly different from the previous one. The difference between these two currents is known as the input offset current. These results clearly demonstrate that the LM741 does not behave as an ideal amplifier, and that its real behavior matches the specifications described in the datasheet. In conclusion, after analyzing the LM741 operational amplifier, we can clearly observe the differences between the ideal theoretical model and the real behavior obtained through simulation. In theory, an operational amplifier is expected to have 0 input offset voltage, 0 input current, and infinite gain. However, in practical situations, these conditions are not achievable due to internal imperfections of the device. For example, in the offset voltage simulation, we expected the output to be exactly 0 volts when the input was set to 0. Nevertheless, the simulation showed a small output voltage of approximately 1 millivolt. This difference is caused by the input offset voltage, which is a non-ideal characteristic resulting from internal mismatches in the amplifier's components. In addition, when analyzing the input bias current, we observed small currents in the nanoampere range at the input terminals. Ideally, these currents should be 0, but real operational amplifiers require a small amount of current to operate correctly. Furthermore, the difference between the currents at the inverting and non-inverting inputs leads to what is known as the input offset current. Overall, the results obtained from the simulations are consistent with the values reported in the LM741 datasheet. This confirms that the LM741 behaves as a real, non-ideal operational amplifier and highlights the importance of considering these parameters when designing electronic circuits. Understanding these differences between theory and practice is essential for achieving accurate and reliable designs in real-world applications. Thank you very much for your attention.